Okay, so we've looked at how to visualize data using ggplot2, and we've also taken a look at vectors, lists, matrices, and data frames. So we've gotten to the point of being able to create and interact with data frames. Now we want to take a look at the dplier tidyverse package that allows us to transform data so that we can obtain just the part of a data frame that we're interested in doing data exploration on or data analysis on. Basically, we want to be able to select subsets of either the observations or the variables, that is, either the rows of the data frame or the columns of the data frame. We may, for some set of observations, want to reorder those observations. We may also want to be able to group those observations into subcategories that we can analyze. Also, where the variables are concerned, often we need to analyze variables that don't exist in the raw data, in the raw data frame. Sometimes we want to manipulate and analyze ratios of two variables or functions of two or more variables. So we may want to be able to create new variables. And we're also going to want to have some way of summarizing the results in our subsetted and reorganized part of the data frame. Okay, so dplier, which apparently does not have an official pronunciation, but I'm given to understand that it's intended to be reminiscent of pliers for twisting and manipulating stuff. And it provides a collection of functions that take data frame objects as input and produce data frame objects as output, so that there's a very, well, tidy is the right term, tidy structure to these things that enables them to work very well both in and of themselves and also together with each other. We have filter and arrange for selecting rows and reordering rows, select and mutate for selecting columns and also adding computed columns that we might need. And we have a summarize function that allows us to compute summary statistics of various kinds for our resulting data frames. We can also group the rows into subsets, subgroups, so that we can do operations on those subgroups. Now, basically, the dplier collection of functions are intended as a streamlined sort of replacement for the apply family of functions that have been in R forever and ever. The apply functions are very powerful, very general, also rather difficult to use, rather difficult to remember all of the various options and arguments that they take. The dplier package, as I said, makes all of this process much simpler by having all of the functions take a data frame as input and a data frame as output and work together collectively. In order to be able to do selections of rows and columns, we need to know about equality, relational, and logical operators. Here is a table of those, ranked from high precedence on this topmost line down to lower precedence. The is equal to and is not equal to test, as well as the less than or equal, greater than or equal to tests, all have the same level of precedence in R. The logical not operator is below that in precedence. The logical and is below that, and the logical or has the lowest precedence of the operators shown here. Now, there is also a double ampersand and a double vertical bar, but those are used for only testing initial values of vectors, not complete vectors. So we don't care about those for what we're trying to do here. And of course, you can use parentheses for changing the precedence hierarchy of a particular expression if you need to. All right, so let's look at the filter function first. And I'm going to pull up my RStudio window so that we can look at several examples involving filters. The filter function takes the data frame as its first argument. That's the input that it reads. Then it takes as additional arguments some selection criteria that allow you to select just a subset of the rows in the data frame based on relationships or relations among column values and comparison of column values to constants or to ranges and so on. What you get back from filter as a return value is a data frame that's going to have exactly the same columns as the input data frame, but very likely a smaller number of rows. Importantly, the input data frame is not changed by the filter function. All right, so to illustrate this, we'll use the built-in MPG test data frame that comes with R. And what we have here are several attributes describing information about various automobiles. Mostly, well, entirely, I believe, from 1999 or from 2008. We have the manufacturer, the model, the displacement of the engine in liters, the year, the number of cylinders, whether it's automatic or manual, whether it's front-wheel drive, rear-wheel drive, or four-wheel drive, etc., etc. Now, I said MPG is a data frame. Actually, within the tidyverse, there is a specialized kind of data frame called a tibble. A tibble is a data frame, but it has had some nice wrapping stuff put around it so that unlike a plain ordinary data frame, you have descriptions of the data types of all the various columns. So here we have character, double, and int as the column types. And by default, when you display a tibble, it will only show you the top 10 rows and then tell you how many more rows there are. All right, whereas with an ordinary data frame, you, by default, get the entire thing if you ask for it, and you have to remember to use a head function to see just the beginning of it. So head will work with a tibble, but the tibble is sort of self-aware and automatically will just give you the top 10 lines anyway. Now, I said that a tibble is a data frame. In fact, if I ask for the class of MPG here, notice that instead of having a single class, MPG has 3 classes. It is a data frame. So any function that can operate on data frames can operate on this MPG tibble. It's also a tibble and a tibble data frame. All right, so it actually has 3 different classes that it belongs to that describe what kind of operations it supports and what its behavior is. All right, well, that's something of a side issue, but I did want to point out to you that anytime you see something claimed to be a tibble, that is in reality a data frame. It just has some extra wrapper stuff around it. Okay, so to use our filter function, we give the data frame as the first argument. And let's suppose that we only want to analyze the records in this data frame for 8-cylinder vehicles. All right, so CYL is the variable that describes the number of cylinders that the engine has. All right, and if I say sil is equal to 8, what I will get back, assuming I have typed this correctly and assuming that that I can compare the cylinders directly to 8, which I can. It tells me here that cylinder is an integer value, and so I can compare that to a number. If I really wanted to be picky, I could make 8 be an integer, but I don't need to for this. What I'll get back is the subset of rows with exactly the same collection of columns or variables, but where cylinder is equal to 8. Notice that I only got 70 rows in this returned data frame, whereas the original data frame, I guess it's gone off the top of my screen a bit here, the original data frame had 234 rows in it. So I've got less than a third of the rows in this data frame pertaining to 8-cylinder cars. If I want to narrow that down even further, following sil equals 8, I can add another filter, another criterion. Let's say I want to look for large displacement 8-cylinder vehicles. That is, I want vehicles whose engines have a displacement of greater than 5 liters. All right, so I'll say sil equals 8, displacement greater than 5. And this is going to give me an even smaller subset. It gave me approximately half of the 8-cylinder vehicles have engine displacements of greater than 5 liters. Okay. Now, the comma here separating the criteria, really you can think of as being like an and in fact you can replace that comma with an and, a logical and. So in this next example, I'm using 3 criteria. I've got my MPG data frame, and I'm saying cylinder equals 8, and displacement greater than 5, and year is less than 2000. So older cars with 8-cylinder engines and displacements above 5 liters. And this gets me all the way down to only 16 records. And in fact, the Tibble data frame type, the data frame subtype, if you will, understands that this will fit cleanly on my screen. So it goes ahead and shows me all 16 records. And tells me that that I have these variables, and I also have one more variable that's not being displayed over here. Actually, I could probably squeeze over my output window there, graphics, my plotting window, and see that final variable as well. Okay. In this next example, just for a little change of pace, I'm using a logical or rather than a logical and. Here I'm asking for cylinders that are less than or equal to 4, or cylinders that are greater than or equal to 8. So this is going to give me the small cars and the big cars. This time there's 151 total rows, so that's about 2/3 of the entire data set, I believe. And the output is in the same columns as what I have for the original data set, but only about 2/3 of the rows. Alrighty. I'm just going to make a remark here that's not really relevant, but normally I try to write code that's pretty cleanly spaced. I would ordinarily, for stylistic and readability purposes, put spaces around my operators. In the course notes, I have not done that for the simple reason that I'm trying to save space on the screen. So what I just noticed that I'm not being very consistent here. On slide 11, I see that I do have a space between the equal sign and the 4. And actually, when I typed in my example up here, I did have a space between sil and the greater than sign. But to save space and to be consistent, in the course notes, I'm not putting spaces around these comparison operators, even though in real life I would do that for readability, and it's probably a good idea to do. Okay, so that's several examples of the filter function that takes a data frame, or in this case a tibble, which is a kind of data frame, as its first argument, and then takes criteria as subsequent arguments. If you give multiple arguments separated by comma, the comma is like an implicit logical and. So instead of using commas, you can use an actual logical and, or in this final case, the example on slide 11, I've used a logical or instead. Now, you can also, rather than comparing variables with fixed values or with ranges of values, you can also compute functions of variables to use in comparisons. Here on slide 12, I'm saying, all right, give me the, let me delete this input here. Give me the MPG data frame where the number of cylinders is greater than the mean number of cylinders. Okay? And I got 149 rows displayed here, which is pretty close to 151. So again, that's roughly twice, or twice, that's roughly 2/3 of the MPG data frame. We can independently compute the mean of MPG's cylinder variable. Okay, so the mean is 5.888 cylinders. So we're getting anything that is a 6 or 8 cylinder vehicle. There are some weird vehicles with 5-cylinder engines. I'm not sure we have any of those. Let's find out. Filter MPG cylinder equals 5. Ah, cool. Yes, we've got some Volkswagens in here with 5-cylinder engines. Okay. Now, all of the examples that I've shown so far, I have not been saving the output. The output appears on the screen, but if I want to save the resulting data frame from calling filter, I can simply assign what filter returns into a variable. So let me have MPG dot C greater than MC. So cylinder greater than mean cylinders. That's not a very good variable name, but there we go. Gets the result of that filter that I did up here. Let me copy and paste this guy. Okay, so now I have an independent copy of that data frame that I can just directly use for whatever analysis and exploration I would like to do. Now, this MPG dataset is, well, unusual is a kind word. Phony or artificial might be a better description, because it has no missing values at all. And in real data sets, that just doesn't happen. Real data sets of any size essentially always have some missing values, sometimes a lot of missing values. So the marker in R for missing values is NA, standing for not available. Technically speaking, actually, each of the basic data types has its own flavor of NA. So there's an integer version of NA and a double version of NA and a logical version of NA and so on. But they all display on the screen as NA, so you don't see the difference when you display data frames with different kinds of columns. Now, pretty much any kind of operation that you do involving NA values will produce NA results. So if I try to do arithmetic or comparisons or logical comparisons, logical operations involving NA, I'm going to get NA. 3 plus NA, 3 plus I don't know what is going to be I don't know what. Hello not equal to NA. Well, NA doesn't mean nothing. NA means we don't know. So if I compare hello to something that we don't know, maybe that missing thing is hello, maybe that missing thing is not hello, but in any case, the result of that comparison is NA. Likewise, false or NA. Now, you could argue here that false or anything ought to be false, but R is very strict about this, and since I'm comparing something to NA, the result is NA. All right? How can you check if a variable's value for a particular observation is NA? Well, you can't do a direct comparison with the equality test or the inequality test. If I say X gets a value that's not available, and then I test whether X is equal to NA, well, the not available that was assigned to X might be some different not available kind of thing than the not available I'm comparing to X. And so R just says, well, sorry, I don't know. And likewise, X not equal to NA, well, that's also not available. Its a result is not available. So what you have to do to check whether a certain value is NA is to call a function is.na, is.na. If I call is.na on this variable X, I get told, okay, that's true. And obviously, I can ask for the inverse of that. So if I say if I say not is.na X, then that's false. What does that have to do with our criteria in the filter command? Well, let me construct a data frame that does have some missing data so that we can see how to use checks for missing data in our filter function. Okay, so what we're going to do here is we're going to create a data frame of patient information for some doctor's office, and there's a little bit more data here than the previous little example that we looked at in the previous lecture. This data frame is going to have 4 columns: age, height, weight, and sex. And we've added a couple more patients, but we forgot to record the age of the first patient and the height in inches of the third patient. So this data frame does have some missing values in it. Let me copy over these vectors to my RStudio environment. All right, so there's my vector of age and my vector of height in inches and my vector of weight in pounds. And the male or female vector. And now I'm going to create a data frame called PATS, patients. Now, again, I mean, this is a sad excuse, but I would ordinarily try to use a very descriptive variable name, but I'm just using PATS to save space. Okay, so let me build this data frame from these 4 vectors. I was very careful to make sure that all the vectors had the same lengths. And now I have the PATS data frame. 4 columns, age, height, weight, and sex, and 7 rows, that is 7 observations of patients with these 4 variables. And I do have a couple of NAs in here. I don't know the age for the first patient, and I don't know the height for the third patient. Okay, there we go. Now, okay. I just noticed there's a typo here on slide 18. This I already created the data frame, so this highlighted stuff here should not be appearing again. When you create a data frame by calling the data.frame construction function and assign that to a variable, the value of the variable does not display. So the value of the variable only displays if you just give the name of the variable. Alrighty. Well, let's use our filter function now on this PATS data frame rather than MPG. And I'm going to ask for just the records where age is greater than 50. Now, in the age column, we have one NA value, and we have other integer values ranging from 22 up to 65. Yes, couldn't read my screen for a second there. So what's going to happen here when we hit the NA? Well, the way that the filter function behaves is it selects the rows where that test is true. So there are 3 possibilities for that test. Either the test is true, or the test is false, or the test is NA. But we're only selecting rows where the test is true. Therefore, if the test is either false or NA, we're not selecting that row. And consequently, this works fine. This first row does not get selected because age greater than 50 here is NA, which is not true. And then these rows where we have ages of 22, 12, 33, and 17, those are also not selected because age greater than 50 is false for each of those 4 rows. But for these 2 rows, row number 3, row number 3. All right, there we go. I knew I could highlight it. Row number 3 and also row number 5, those are the 2 rows that are selected. In this case, the returned data frame of just those 2 rows is displayed on the screen because I did not assign that returned data frame into a variable. Now, where I run into trouble is if I try to ask for something like the mean age. So let me filter my PATS data frame and get all of the records where, all of the observations or rows, excuse me, where the age is greater than the mean of the age variable. Now I'm getting 0 rows. What's going on there? Well, My problem now is that the mean age is the mean of these values, and one of those values is NA, so any calculation that I do involving an NA is going to result in NA. Okay, so in PATS, age is a column. Age is a variable. And if I ask for the mean of PATS $age, I get NA. Consequently, what I'm doing here is I'm comparing whether age is greater than NA, and the result of that test is always NA. So despite that I have 7 rows of data here, I end up getting 7 NAs for the tests of age with the mean of age, and therefore I get no rows being selected. So I somehow have to eliminate the NA data value from that age column. Well, actually, there's a little more to it than just that. I have to consider first whether the age column has so many NAs in it that the whole concept of the mean age is reasonable or silly. In this case, I've got 7 records and I've got 1 NA, so from a data exploration standpoint, I'm willing to believe that the mean of the ages is going to be close enough to the mean of the 6 ages that I do have. So I'll go ahead and just ignore the NA and compute the mean age using all of the non-NA values. All right, so let's see how we go about doing that. How can we get rid of the rows for which is.na of age is true? That is, all of the rows where age is not available. All right? One way we can do that, which I always get backward, and so I don't like to do it this way, is to add to the mean function call an additional argument. na.rm is true. So na remove is true, meaning that the mean function will simply ignore all of the records, all of the values in this age column, in this age vector, that have NA set. Now, since to check whether something is NA, you say is.na, invariably, I always say rum.na equals true. And the frustrating thing here is, if I say mean of PATS $age, rum.na is true. Wait a minute. I said to remove the not. I said to remove the NA values, and I'm still getting NA. Ah, rats. Well, it's because I spelled the thing wrong. And one of the things that's frustrating here about a lot of these functions in R is that you can pass them any old arguments, and if the arguments aren't recognized, they're just ignored. So I don't have the benefit here of being told, no, you idiot, you meant to type na.rm, not rm.na. It just doesn't work. So I don't know until I test the thing whether whether I typed the correct thing or not. So I needed to have said PATS $age, comma, na remove is true to get that to work. All right. In any case, it does work. So let me use that with my filter function. So this time I'm going to say filter PATS and I need to put spaces in here because it looks wrong to me otherwise. All right, so I'm going to filter the Pat's data frame to select the rows where age is greater than the mean of the ages where we have removed the NA values. And poof, I get what I would have expected. All right, now it's easy for me to tell that this is what I would have expected because this data frame is so small, but if this data frame had thousands of records in it, it would be a lot more difficult for me to verify that the rows that I got are actually the correct rows that I wanted. Alrighty. So that's one way. Now another way is to apply the filter function 2 times. Okay, I can say Pat's with age, in order to save the result of the first filter, filter Pat's such that age is not NA. All right, so that's going to get rid of all of the records, all of the rows, excuse me, all of the observations where age is NA. All right, notice that Pat's has 7 records in it, one of which has NA for the age. When I do this filter saying, give me all of the rows in Pat's where the age is not NA, the resulting data frame only has 6 rows in it because that first row that had NA is tossed out, filtered out. Now I can do another filter by using Pat's with age as my input data frame, my argument data frame, and now I can test for age greater than the mean of age, if I spell it correctly. All right. So I did one filter to get rid of the NA values, and now I'm doing another filter to get the ones where the age is greater than the mean of the age, and this gets me what I wanted. All right, now we can argue that this thing I did up here, using the additional argument na.rm equals true to the mean function, got me there quicker. And indeed it did. It got me there in 1 step instead of 2. But it's also more information to remember and more stuff to type. Well, it's seeing what we've done so far, it doesn't look like it's more stuff to type. But one of the advantages of the so-called tidy approach using these half a dozen manipulation functions, transformation functions, is that you can accomplish more while at the same time knowing less. And I'm a huge fan of accomplishing more while knowing less. I think that's a very, very great trade-off. Now, one bad thing about what we just did here is that we had to create this intermediate variable, Pat's with age, by taking the return value from the first filter and using that as the argument to the second filter. So that's clumsy. We don't really have any need for this Pat's with age variable now. So let's see if we can smooth that out even more. Well, we can simply nest the filter function calls to avoid the need for that intermediate variable. That is, instead of calling filter with Pat's with age as the first argument, since the filter function returns a data frame, I can simply use a nested call of the filter function that produced Pat's with age. All right, so I can say filter the result of filtering pats for not na of age. All right, so there's my inner filter. Now that inner filter there, which I have highlighted in blue here on my slide, that inner filter function call is going to be called first, and it will return a data frame as its result. That data frame is then passed down to the outer filter function as its first argument, and my test at this second level, the outer level, is whether the age is greater than the mean of the ages. And there I get my same result. Now even as far as typing goes, we're getting pretty close to what we had up above. And we don't need to know as much. All right? If we just remember about is.na, we're good for testing whether something is not available. We don't need to remember about not.rm versus room.na versus whatever. All right, well, this is good. This is better, but it's kind of ugly now to have to do this nested function calls. So let's see if we can improve that even a little more. It turns out that part of the tidyverse is the use of pipes to pass the data frame from one function and make that the input to another one of the tidyverse functions. And the pipe operator, which actually originated before the tidyverse, but the tidyverse stole the idea very, very gratefully. Percent greater than percent is how you create a so-called pipe in R. And if you are used to using command line tools in a Unix or Linux environment, this concept of pipes and hopefully something about the power of pipes will be something that you're familiar with. In any case, within R, if I call a function that expects a data frame as its first argument, followed by some additional arguments, I can rewrite that to use the pipe symbol by giving my data frame first and piping that data frame into the function with just the trailing arguments. Let me prove that that's true. So here I have MPG, and if I say filter MPG model equals A4, I get the 7 records for Audi A4s. As an alternative, I can use a pipe. I can say MPG piped into filter where model equals A4. These two notations internally mean exactly the same thing. This notation where I'm using the pipe internally gets converted into using MPG as the first argument. And I get the same result. Why does this matter? Well, it matters because you can generalize this and use it in place of a hierarchy of nested function calls. All right, so if I have some tidyverse function, the only one we know so far is filter, but we'll get to others. So if I have some tidyverse function and I call that function with the result of some other tidyverse function as its first argument, well, what I can do is I can pluck out that nested function call and put that in front of a pipe with fun1 and the trailing arguments after the pipe. And for that first function, I can also take the data frame out in front. I can take the data frame in front and I can pipe that into fun2 with its selection args, into fun1 with its selection args, and so forth. So I have a data frame going in to fun2, which returns a data frame. That data frame goes in to fun1, which returns a data frame. So to make this general recursive unwinding of these nested calls specific, let's take a look at the nested call that I made up here. All right, let me copy and paste that back down. Okay, so there's my nested call. Now let's unwind this thing. So Pats is the data frame that I'm trying to analyze. Let me pipe that into the filter that is going to get rid of the missing values. And then let me pass that through the pipe into the filter that is going to select the rows where age is greater than the mean of the age. Shazam. Okay, so poof, I got the same result. And this version okay, now you're gonna complain and deny it and be upset initially, but once you get used to it, this version is easier to read. It says, take Pats, then filter out the missing values, then filter out, or filter in, if you will, the rows where the age is greater than the mean of the ages. Okay, so start with Pats, then throw away. Well, let's try to be consistent. Start with Pats. Select the rows where the age is not missing. Select the rows where the age is greater than the mean of the ages. And there we are. And this you can chain along for many functions in a row and make sense of each of the transformations as they're going along. So cool stuff. All right. Now, typically people don't do this entire unwinding to just have the data frame as the first thing in the R statement. It's a stylistic difference, but generally what you'll see is that people will put the original data frame as the argument for the first filter function, and then take the output of that first filter function, whoops, wrong keys, and filter and feed that through a pipe into the next filter function or whatever other tidyverse function we want that to go to. Okay, so that's a more common style, although they're equivalent. I mean, by definition, they're equivalent. Now, of course, to retain the result of this pipeline, the assignment operator has the lower precedence than this pipe stuff, so I can just give a variable name and the assignment operator, or the gets operator, and that will capture the output of the entire pipeline, which is the resulting data frame, and put that into this variable. There we are. Okay, so what have we done? We have introduced the collection of tidyverse functions that we can use for transforming data frames. We can select rows, reorder rows, and group rows. We can also select columns and add columns if we need to. And we're going to investigate the other 5 functions in the dplyr package in the next part of the lecture. So there we are. So we've also introduced the idea of using pipes to chain together a sequence of these tidyverse transformation functions. Alrighty.